I want to give you a quick introduction to second derivative. This video should be the shortest, the fastest, and the easiest approach to second derivatives. Let's start from derivative notation. So for second derivative, let's start from second derivative first. So for second derivative, very quickly, that is y prime f prime of x, or you can call that dy over dx, which is the derivative of y with respect to x. You can pull the y out, so the derivative of y with respect to x means we are treating x as an independent variable. And then for the second derivative, so instead of having 1 prime, so now we have 2 prime. So this is not, don't call this y prime prime, we call this y double prime, so that is f double prime of x. For the dy dx, we add a 2 for the d, we add a 2 for the x, so this is the derivative of the first derivative. So we have the derivative with respect to x of the first derivative. So this dy dx is the first derivative. So you have a function f of x, you take the derivative of that, and then you take the derivative again. So you have function f of x, you take the derivative first, and then you take the derivative one more time. So this dy dx is the first derivative. So after this is done, you take the derivative of the result again. So this second derivative is the derivative of the first derivative. So do we have higher derivative? Of course we do. You can try triple prime, so y prime prime prime, and then f triple prime of x. So for triple prime, we add a 3 for the d, and then we add a d for the x, and then the fourth prime. So why we don't write 4 primes, we write a 4 in parentheses. We have to write this parenthesis because we don't want to mix this up with the exponent. So f fourth prime of x, so add a 4 to the d, add a 4 to the x, you can go to the nth derivative. So y to the nth derivative, f to the nth derivative of x, so 1n for the d, and then 1n for the x. But in calculus, we mainly use first and second derivative. What do the first derivative tells us? So for the first derivative, what are you trying to study? So the answer is slope. So for first derivative, we are trying to study slope. So let me give you a quick example. So before we get into that, I built a table. So for the first column, I have interval, and then the second column, I have derivative. So let's say we have an interval x is between a and b, and then f prime is greater than 0. The first derivative is greater than 0, is in this interval. What does that mean? That means the function is increasing. The slope is positive, means the function is increasing within this interval from b to c. So let's say f prime is less than 0, the first derivative is less than 0, that means the function is decreasing within this interval. And then the best case to explain this table, or to add some real numbers to this example, is to use the parabola f of x equals to x. So for the first derivative, you can use whatever method you want. Either you go by the limit definition of derivative, or you take the shortcut. I will just take the shortcut. So the shortcut is f prime of x, or you can call this dy dx. How do you do the shortcut? The shortcut is you bring the 2 down to the front. And then how about the power? The power is 2 minus 1, which is to the first power. So 2x is the first power. So let me give you some numbers. So what happened when x is equals to negative 3? So what happened when x is equals to, I should say, what is the slope of the parabola when x is equals to negative 3? So the slope is, you plug in negative 3 to the first derivative, 2 times negative 3, this is a negative 6, this is negative. That means the function is decreasing when x is equals to negative 3. And then what about x is equals to 4? So this is 2 times 4 equals to 8, that is greater than 0. That means the function is increasing when x is equals to 4. And then what happened when x is equals to 0? So when x is equals to 0, 2 times 0, this is equals to 0. That means the function has a horizontal asymptote. Sorry, not horizontal asymptote, horizontal tangent line. At this point, 0, 0. So what happens if you plug in x value to the f of x? If you plug in an x value, so let's say x equals to 5, then you have phi squared equals to 25, right? Then phi comma 25 is the xy coordinate, is an ordered pair, is a point on the parabola. If you plug in a number to the original function f of x, then you get a point on the curve. If you plug in a number to f prime of x, you get a slope of the curve at that point. Let's draw a picture. So the picture that we have is the parabola. So let's draw x-axis and then y-axis. And then here is my parabola. Okay, so here is my parabola. So when x is equals to negative 3, so we have a point right over here, right? So I don't really care about what the y value is. When x is equals to negative 3, I can see that the first derivative is negative, is decreasing. That means at this point, the tangent line is going downhill, decreasing. So, and then when x is equals to 0, we have a horizontal tangent, and then at x equals to 4, we have this point, and then the first, oh, I forgot a prime, right? The first derivative is equals to 8 positive, so that means the tangent line is going up. So that's what the first derivative tells us, and then you already studied this in the previous lesson or the previous video. And how about second derivative? Oh, for the second derivative, before I start telling you what the second derivative is, I want you to specify that for this higher derivative, the n must be greater than or equal to 1 because the minimum is first derivative. There is no 0 or negative 1. The minimum is 1. Okay, and then the n must be an integer. There is no 1.5. First derivative, second, third, fourth, fifth, sixth, seventh, 8, 9, 10, 11, 12. Okay, now back to our business. What do the second derivative tells us? The answer is, this is a new key vocabulary here, concavity. Okay, the second derivative tells you the concavity of a function, concavity. Right? So let's go over the table. So we have two columns, one for interval, one for the first and second derivative. So for the interval, I use two intervals, x between a and b, x equals to b. I know that it's not an interval, but we need this point. And then x is between b and c. And then I gave you the first derivative. Between a and b, the first derivative is less than 0. That means the function is decreasing. Again, we are talking about first derivative. So that is a matter of increasing, decreasing, and horizontal tangent. Equals to 0, then you have a horizontal tangent. And then greater than 0, the function is increasing. I'll just write INC, increasing. And then for all of this, so for these three derivative, look, I said that f double prime is greater than 0. I want you to take a look. First derivative negative, decreasing. First derivative 0, horizontal tangent line. And then first derivative greater than 0, increasing. So for all of these three derivatives, I said that the second derivative of all of them, okay, is greater than 0. So second derivative greater than 0, that means the function is concave up. For concave up, the best picture to think about concave up is an parabola that opens upward. So this parabola opens upward, is a bowl that is facing up. I call this concave up, and this parabola is between a and c, a, b, and c. I use this interval. When x is equals to b, we have a horizontal tangent line, and then from a to b, the function is decreasing, right? So this function is decreasing. And then from B to C, the function is increasing. So here is how the concavity works. You have a decreasing, you have a horizontal tangent line, and then you have an increasing. So for this decrease, horizontal, and increase, we have a concave up. How about concave down? So for concave down, I would need to introduce another three intervals. So for concave down, I have x between A and B, at B, and then between b and c. So between a and b, I have derivative, first derivative, greater than 0, first derivative. Okay, so that is increasing. First derivative equals to 0, that is a horizontal tangent line. And then first derivative less than 0, so this is a decreasing. And then for all of this first derivative, I said that the second derivative is less than 0. So that means the function is concave down. Again, I have all these threes. These are the three first derivative, right? All three of them. For the second derivative, they are all less than 0. So for this function, between this interval, the second derivative is less than 0. That means the function is concave down. Concave down, I will think about that as an upside down parabola. So that is concave down. From A to B, you have increasing. At B, horizontal tangent. B to C, decreasing. So as long as you have this pattern, increasing, horizontal, and then decreasing, then this curve is concave down. Concave down. Okay, so down, horizontal, and up, we have concave up. And then up, horizontal down, we have concave down. So concave down. Let's put this here. Okay, and then for concavity, there is one more point that you have to know that is called an inflection point. Inflection point is where the concavity changes from up to down or from down to up. These are the two pictures. So the first one, I have a concave up and then concave down, right? So opens up and then opens down. And then the point where the up and down changes, that is called an inflection point, or it can be going concave down and then concave up. That is where the concavity changes. That is an inflection point. To be honest, if you just look at a picture, just find a picture from a textbook, they ask you to find the inflection point and then tell the concavity. To be honest, if you just look at the function, it is pretty hard to tell. So if you just look at, they give you some curve, right? And then they break this down into interval. And then they say, okay, in this interval, concave up or down, that interval, concave up or down. Can you tell me where the inflection point is? To be honest, it's pretty hard to tell if you just look at it. But if you do the math, everything is super clear. So that's why I have to give you this example. And I said that inflection point is hard to see. If you just look at the graph, it's hard to see. Okay, just like this. If I ask you to use your eyes to measure 2 grams of sugar, just use your eyes, just grab it. Just grab 2 grams of sugar and then look at it to tell me if that is a 2 grams or not. That is pretty hard if you just like look at it and tell is that exactly 2 grams or not. Okay, back to our business. So we have x to the third power, and then this is the graph, and then I will switch to the first and second derivative. For the method, you can use any method you like, either the limit definition or the power rule. I prefer the power rule. The power rule is easy, so you find the first derivative. The power rule is you bring the 3 down, all right? You bring the 3 down. That is not tough to do. You are taking calculus right now. You bring the 3 down to the front of x, and then 3 minus 1 is the second power. That is not hard to do, right? And then you take derivative one more time, second derivative. You bring the 2 down. So we have, you bring the 2 down to the front, right? So you have 2 times 3. That is equals to 6. Again, you bring the 2 down to the front, and then you multiply the 3. 2 times 3 is equals to 6, and then 2 minus 1 is equals to 1. So this is the second derivative. And then for the inflection point, the inflection point is where the second derivative equals to 0. So I should add one more thing. So for inflection point, that means the second derivative equals to 0. So you let 6x equals to 0. So that tells me x is equals to 6. And in order to prove this, you have to do a test the intervals. So this is our number line. I have 0 in the middle, so that breaks the line down into 2 intervals. One from negative infinity to 0, and then one from 0 to positive infinity. And then you have to pick a value just for the first interval. Pick any value within the first interval. Don't pick the 0. You can pick -1, -2, -3, anything you like. So I will just pick -2. So this is f double prime of -2. That is equals to f double prime -2. That is 6 times -2. That is less than 0. I know that is equals to -12, but I don't really care. I need to know that it's positive or negative. And then this one, you can pick a 1 or you can pick a 3. So I will just pick a 3, or you can pick a 10. 3. So that is f double prime of 3. So that is 6 times 3 equals to 18, greater than 0. What does that mean? We just talked about it. First derivative negative, that means is the function is concave down. And then greater than 0, so this is concave up. What does that mean? This is concave down, this is concave up, and then at 0, that is where the up and down changes. So when x equals to 0, y equals to 0, just look at the graph, and then this is inflection point. Go back to the graph. This is from negative infinity and then all the way to 0. So we have a 0 right here. This piece is concave down, and then this piece is concave up. So the best way to check out the concavity and the inflection point is you look at the second derivative. And then one more time, the first derivative tells you increasing, decreasing, horizontal, asymptote, but the second derivative tells you concave up, concave down, and inflection point, which is the concavity of the function. All right, so that is the end of the video. So that should be the shortest, the quickest, and the easiest way to understand second derivative and concavity. If you like it, give me a like, and I will see you all in the next lesson. Signing out.